Okay, we'll do some more of section 7.2 here. At the moment, we were looking at using the table in reverse. And so what I mean by that is that we're given an area or a probability, and we want to find a z-score that correlates to that area or probability. We're on problem 12 here, where it says find a z-score such that the area under the standard normal curve to the right is 0.95. Okay, so I've set up my picture. Here's the z-axis. The mean is at 0 right in the center. You have to figure that the z-score that we're looking for is going to be to the left of the mean, because if I shade that area that is to the right, we're looking at 95% of the region that is to be shaded. Okay, now if I were to mark that number over here and then shade this little sliver, that wouldn't look like 95% of everything underneath the bell curve. Okay, so I'll expect to have some negative z-score here when I get my answer. Table only gives area to the left, and so I don't want to be looking for 0.9500 in the chart. I want to be looking for 0.0500. That is the area to the left. Okay, so I'll go to the chart now, and 0.0500 is not listed. And remember that it's typical to see that the area probability is not there, so you're just going to take the closest number. Now in this particular situation, we don't have a closest number. 0.0505 and 0.0495 are the exact same distance away from 0.0500. So it wouldn't be right for me to take one z-score over the other. Like, it wouldn't be right for me to take negative 1.64 or negative 1.65, since these two numbers are the same distance away. Okay, now this is going to be a rare time where the z-score that we'll want to give here is going to be a 3-digit decimal and not a 2-digit decimal. I'm going to go right in the middle of negative 1.64 and negative 1.65, and I'm going to call it negative 1.645. Okay, and that's my answer. Now, again, this usually doesn't happen. You know, usually when you're using the table in reverse and the number's not listed, there's going to be a definitive closest number, and you just simply pick off that number and go to the answer. Okay, but we don't see that here. Whenever you have two numbers that are the same distance away, you're going to average the z-scores. Okay. Here's some notational stuff next. And a note, the notation z sub alpha is the z-score such that the area under the standard normal curve to the right of z sub alpha is alpha. Alpha is a Greek letter. That's a lowercase alpha in Greek. We're going to need to know this notation later when we get to chapter 9 and we talk about confidence intervals. Okay, so problem 13, we want to find the value of z sub 0.15. Alpha is 0.15 in this problem. Alpha always represents the area to the right of a z-score. Okay, so this problem here is just like the other two problems that I've been showing you. We're wanting to find a z-score, and we'll be using the table in reverse to get that. 0.15 is the area to the right of this z-score that I'm supposed to look up. Okay, so I have to figure that I'm on the right side of the mean, because if I were to position that over here on the left side and shade to the right, that is already going to be more than 0.5 of the region, you know, since the area to the right of 0 is 0.5 and 0.15 is very much less than 0.5. Okay. Table only gives area to the left, so I need to be looking for 0.8500. Use the complement rule to get that. And let's see, 0.8500 is, again, not listed. 0.8508 would be the closest number that I see. And 1.04 would be that z-score then when you match up the row and column. So 1.04 would be my answer. I indicated the number that I'm using there. You could also write z sub 0.15 equal 1.04. That means the same thing. You're still talking about a z-score in this notation. So this problem here is really not anything different than the other two problems that we've looked at in the notes. Okay, it's just really kind of a introduction to a notational thing that we'll see later down the road. All right. The next thing that I want to show you is just some typical calculations that you'll be seeing when we start looking at the application stuff. Right now, we're just kind of getting some used to the table, but there, we'll be doing a bunch of applications as well in this section. So assume that the random variable x is normally distributed. Okay, that means that I'm looking at a histogram, and the shape of the histogram is bell-shaped and symmetric. The mean is 50, and the standard deviation is 7. We're going to do the following calculations. Now, the first thing always is to convert the variable x to a z-score. That is always going to be step one. Now, in this notation here, I'm using probability notation. Z is found by computing x minus mu over sigma. Okay? In this notation here, the symbols are going to stay on their side of the inequality, and the numbers are going to stay on their side of the inequality. All right? So step one is to change the variable. I'm going to say this is equal to the probability that x minus mu over sigma greater than, now I'm going to do the same thing on the right, only I'm going to use the actual numbers. 65 is my x value. I'm going to subtract the mean, which is 50, and then divide by the standard deviation, which is 7. 65 minus 50 is 15. 15 divided by 7 would be 2.14 if you go to the nearest two digits. Remember, z-scores always go to the nearest two digits. X minus mu over sigma, that's what I'm calling z. So now I have changed the variable, and now the problem becomes like it was that we were doing before. Okay. Notice how I'm not ready to go to the table because I'm talking about area to the right. Table only gives area to the left, so the next thing would be to use the complement rule. Take 1 minus the area to the left of 2.14. Be sure that you switch the sign. And remember, equal signs don't matter, so if I did not have this and it was just strictly a less than, that would be okay. Still make sure that you switch the sign, though, so because you're talking about area to the left. Now we're ready to go to the table and look up the area to the left of 2.14. So here's 2.14. Let's see, that I'm getting the area to the left is 0.9838. 1 minus 0.9838 is 0.0162, and so 0.0162 would be my answer. The probability of being greater than 65, we don't know what x represents here. They're not telling us that. But that probability is 0.0162. Okay. Problem 15 is another one. I want to find the probability that x is less than or equal to 58. Okay, well again, equal signs don't matter, so you can lose that or keep it, doesn't matter. But still, step one is going to be to change the variable. So let's change x to z using the formula for a z-score. Of course, make sure that the probability sign is there. So I'm going to want the probability that x minus mu over sigma less than, I'm do the same thing on the other side, but I'm using the actual numbers. X is 58 minus the mean, that's 50, divided by the standard deviation, that's 7. 58 minus 50 is 8. 8 divided by 7 is 1.14 if you go nearest two digits. X minus mu over sigma, that's what I'm calling z, and so now I'm looking at the probability that z less than 1.14. I have now changed the variable from x to z, and at this point, I can now go to the table because I'm talking about area to the left, right? So I don't need a complement rule like I did in the last problem. And this one, we're already talking about area to the left, so let's go to the table and we'll look up our answer. The area to the left of 1.14, here's 1.14. When you match that, I'm getting 0.8729. 0.8729 is my answer. Okay, so the probability that x is less than or equal to 58 is 0.8729. Again, we don't know what x represents, but this is really just kind of a computational exercise here. Of course, like anything else that we've been doing with the probability notation, make sure that the probability notation looks good. I would be very, picky about this still in class. I'd be indicating this in class. Make sure that you've got the probability sign. Some people won't write the probability sign, and if you don't do that, that's a problem, right? Because then you're saying probability and z-scores are the same. They are not. That will lead to massive confusion down the road if you make that mistake. Okay, so we need the probability notation. Of course, lose the probability notation when you calculate your probability. Be sure that you know which way the sign is to be facing. Don't just write probability of 1.14. That probability would be 0, right? So there'd be a notational issue. Notation is important, just like everything that we've been doing. Okay, problem 16. I want to find the 80th percentile rank. Let's go back to chapter 3 for a moment and remember percentile ranks. A kth percentile rank is a number such that k% of the data is less than or equal to that number. Okay, so in this problem, I want to find the 80th percentile rank. What that means is that 80% of the data is going to be less than or equal to what number? Now, this is not a probability question. I want to find an x value such that 80% of the data is less than or equal to x. Okay? Not a probability question. Now, anytime that you're computing a percentile rank, you're going to be using the formula for a z-score, but when it has been solved for x. So here's the formula for a z-score, right? Z equals x minus mu over sigma. And I've solved this equation for x to get x equal mu plus sigma times z. Now, in this problem, I already know mu and sigma, right? Mu was 50 and sigma was 7. So really all I have to do is find my z-score and then plug in all three of those numbers to get x. Well, again, a kth percentile rank is a number such that k% of the data is less than or equal to that number. Now, is less than or equal to is keywords in the definition there because in a way they're describing area to the left. All right, so in this problem here, I want us to find our z-score, but we're going to be using the table in reverse since they're telling us the area to the left of this z-score is 0.8000. Okay, well, let's go to the table, and I'm looking for 0.8000 in the group of numbers. That is not listed. Okay, points, and remember, that's typical. Okay. Use the closest number to the one that you're given there. 0.7995 is the closest to 0.8000. So we're going to use that number instead. Okay, when we match up the row and column, we're getting 0.84 as our z-score. Okay, and I've indicated the number that I'm using there to get that z-score. So, okay, we have everything now to get x. X is equal to mu plus sigma times z. Mu is 50. Sigma is 7. The z-score is 0.84. We just looked that up. And so then when I go to the calculator, 50 plus 7 times 0.84, I'm getting 55.88. That's my answer. Now, if they were asking for an interpretation, this is the 80th percentile rank, which means that 80% of the data is going to be less than or equal to 55.88. Okay. By the way, just an observation here, 80% is less than 87.29%, right? So before I did anything, like I probably could have figured that x is going to be some number less than 58, all right? Since 87.29% of the data is less than or equal to 58, okay? And that's exactly what happened. Now remember that a percentile rank is a whole number value here. We've got the 80th percentile rank. But in this problem, they're just simply asking for a number, an x value. It's not a probability question. All right, at this point, I would like you to look at the problems that are on page 347. Only do problems 1 through 35. There is still more to talk about in this section. I mentioned that 7.2 has quite a bit going on in it. Right now, we have just looked at how to use the table forwards and backwards, and also just kind of some typical calculations that we'll be doing. And now that we've got that done, we'll kind of turn our attention to the application stuff next, but we are still in section 7.2. At this spot, I'd like you to know this information for upcoming quiz, and the application stuff that I'll be starting on the next page of the notes will be on your next quiz then. Okay, and I'll reemphasize that in Blackboard. All right.